So here we are on question 2. So question 2 is a logs question for part A and B, and then finishes with induction. So a good few students would have looked at this and said, I'll move on. However, with practice, these can definitely be mastered. And a lot of students, if you're H1 students, you'd be hoping to get 30 out of 30 in questions like this. Okay, let's have a look at it. So part A, write the expression 5 times the ln of 2, so log 2 to the base e, plus a half times ln of 16 minus the ln of 8 in the form ln of k. So you'd remember, of course, obviously, as I mentioned, that ln is log to the base e. So all three of these are dealing with the natural log to the base e. With questions like this at the start, you might be wondering, okay, how am I going to do it? You remember page 21, of course, are where all your rules of indices and logs are. So you might be thinking to yourself, okay, it's going to be, I'm not quite sure what to do, but I do what I know. Those 3 rules here are going to be your key ones. That, what we have is what we call the multiplication law in logs, that if you have log x times y to the base a, you can call that log x to the base a plus log y to the base a. So that looks like it could be similar here because you're adding 2 logarithms of the same base together. Similarly with the division law here, log x over y to the base a, that's log x to the base a minus log y to the base a. And in time, it looks like that could come into play here because you have a subtraction. However, we also have the part here where we have numbers in front. So we have 5 times ln of 2. So that looks a bit like here. If we have q times log x to the base a, well, I can say that's log x to the power of q to the base a. So that the number in front can go as above the power. Okay, so let's have a look and see how that all helps us. So as I always say, even with these, looking at it for myself, I could be looking at say, well, how can I exactly get my answer into the correct form of the ln of k? But I'm just going to start. So what I'm going to do is I'm going to get rid of this half first before I do anything else. So I'm going to bring him, again, using the third law of logs. I'm going to now say a half times log 16 to the base e is log 16 to the power of a half to the base e. Power of a half, of course, is square root. So the square root of 16 is going to give me 4. Similarly, what I'm going to say here is the ln of 8. Well, I know that 8 is 2 to the power of 3. So now I can say ln of 8 is ln of 2 to the power of 3. Now, the reason I'm going to be doing that is because I'm kind of thinking to myself, because I have to get an answer in ln of one number, because of that, I should try and get the same number here. And 2 is most likely to be the correct one, because 2 is 2 to the power of 1, 16 is 2 to the power of 4, and 8 is 2 to the power of 3. So there's a connection there between them. So I keep going, I keep kind of working on it. So I'm going to say, okay, 16 to the power of a half is 4. So now I have ln of 4 here. I have the ln of 2 to the power of 3, and I can use my power to the front rule. So I have 5 ln of 2 plus the ln of 4 minus 3 times the ln of 2. And even at that, if I wanted here, I could just do this to the side. I could say 5 times the ln of 2 minus 3 times the ln of 2. Well, that's just like saying if I have 5x minus 3x, I know I'd have 2x. So here I'd have 2 times the ln of 2. So I could do it that way, or I can keep going here and I can say, well, ln 4, okay, the ln of 4 is ln of 2 to the power of 2. And again, now I can use my power to the front rule here to bring 2 to the front. So I'm going to have 5 times the ln of 2 plus 2 times the ln of 2 minus 3 times the ln of 2. So in fact, now I can actually get very close to my answer straight away here. by saying, well, I got 5 lots of something plus 2 lots of that same thing minus 3 lots of it. 5 plus 2 is 7, take 3 is 4. So I have 4 times the ln of 2. And I might say to myself, oh, I have it done there, but I look back up here and say I have to get it in the correct form. So again, I'm going to use the third law of logs. 4 times ln of 2 is ln of 2 to the power of 4. And of course, that is ln of 16, log 16 to the base e. So that's my answer. So I could have, as I said, used these first rules up here. The way I went around it, I didn't have to. But if you did it that way, there's no problem at all if you got to the correct answer. So ln 16 for 5 marks. That brings us on to part B, solve. So in the first case, we were just writing it or simplifying it. In the second one here, we're solving. So as my students know, I say, how do we solve any equation? The first time I ask it, people give all sorts of answers. After a while, they all say you isolate the variable. Our variable is x, so we must do it step by step. So again, we look at our page 21. This time, it certainly does look like I'm going to use rule 1 here at the start. So I'm going to say that I can say to myself that because I'm adding together 2 logarithms with the same base, I can do it. I can add them together to get 1 logarithm, and I multiply the 2 powers together. So I get x times 17 minus 3x. So log x times 17 minus 3x to the base 10 is equal to 1. Now I'm going to use what I call the key rule of logs, which says that if you're going from indices to logs or vice versa, the base remains the base and the other 2 switch. Okay? So in my case here, what's going to happen is I'm going to end up with like 10 to the power of 1 equals x times 17 minus 3x. And of course, I can multiply that through. Because what's happening is when I go from logs to indices, same the other way around, if it was indices to logs, the base stays as the base. So the 10 stays as the base. What was the answer will switch to be the power, and what was the power will switch to be the answer. So that's what we get there. We multiply it out, simplify it down. We're down to a quadratic equation. How many times do quadratic equations come up? Very often is the answer. Now you could use minus b, or you can factorize. You're going to get 3x minus 2 equals 0, or x minus 5 equals 0. X equals 2/3 and x equals 5. And if you test both answers, you'll find that they both work. So that's your answer for 10 marks. So again, people might have been a bit worried about that question at the start, but it's not too bad. We then go on to induction. Prove by induction that 2 to the power of 3n minus 1 plus 3 is divisible by 7 for all n, an element of the natural number. So for all natural numbers, we have to prove that 2 to the power of 3n minus 1 plus 3 is divisible by 7. So, well, as we know in induction, regardless of whether you're doing it in Leaving Cert or doing it in college, you know, it always has the same process. You start it off with making sure it's true for what we call the base case, the lowest possible value. So in this case, because it's true for all L, an element of the natural numbers, all natural numbers, the lowest natural number is 1. So we're going to prove it's true for n equals 1. So we're going to put in 1 where we have n. 2 times 3 is going to, or sorry, it's 2 to the power of 3 times 1 minus 1. Well, 3 times 1 is 3, minus 1 is 2. So what we're going to have there is 2 to the power of 2, which will give you 4. And then 4 plus the 3 will give you the 7. And of course, 7 is divisible by 7. So it is true for the base case. So true for n equals 1. Then after that, we're going to go to our second step. We're going to assume that it's true for n equals k. So what that means is 2 to the power of 3k minus 1 plus 3 is divisible by 7. So we're going to say it's equal to 7 times some number, where that number is a natural number. So we're going to say it's equal to 7a. Now you can do this slightly differently. Your teacher could show you a different way to do that. That's absolutely fine. So I'm saying it's equal to 7a. Now what we're going to do is this. We're going to prove it's true for n equals k plus 1. So we've proven it's true for n equals 1, assumed it's true for n equals k. We're going to prove it's true for n equals k plus 1. So where we had k originally, or where we had n originally in the original part, we're going to be putting in k plus 1. So again, instead of k, it's k plus 1. So you just got to be a bit careful with your multiplication. Now, I've seen people make mistakes here. You're multiplying 3 times k to get 3k, 3 times 1 to get 3, but you're subtracting the other 1 from that. So you're going to end up with 3k plus 2 equals. So you're going to end up with 2 to the power of 3k plus 2, and you still have your plus 3 here with it. So now sometimes people get a bit stuck here. They're not quite sure what to do. So at all times, you're thinking you need to prove that this is divisible by 7, right? That's what we're trying to do. And it is always true. Again, in secondary school, in third level, it's always true. You always use step 2 to prove step 3 in induction. So what are we going to do? You're going to try and make what we have here look a little bit like this, so we can use step 2. So the big difference here, of course, is we have this plus 2 here. So what I'm going to do is I'm going to say, well, I could say, if I said, okay, I know what I had originally here was a minus 1. So if I add 1 and subtract 1 there, right? Well, plus 1 minus 1 is 0. So that's not making any difference in real terms to what is there, but it allows us to say, and I'll just add in one last little bit, is that you'd have 2 to the power of 3k minus 1 plus 3, okay, because minus 1 plus 3 would give you that 2. And you, of course, you still have your other plus 3 hanging around there as well. But then I can use my rules of indices. And I'll just remind you here, because I know this is the key bit that sometimes people get stuck on. Like if you have a to the power of b times a to the power of c, you can say that's a to the power of b plus c. So you can do it the other way around. If you have a to the power of b plus c, you can say that's a to the power of b times a to the power of c. And that's what we have here. We have 2 to the power of 3k minus 1, but we also have the plus 3. So we can say, okay, that's 2 to the power of 3 multiplied by 2 to the power of 3k minus 1. And we still have our other plus 3. 2 to the power of 3 is 8. So we have 8 times 2 to the power of 3k minus 1 plus 3. Now we're getting close, right? But we're not quite there. We have the 2 to the power of 3k minus 1. Okay, that's good. We have the 3. That's good. But what we have, which ain't so good at the moment, is this 8. Now, this is where practice comes into play. A student might say, like, how am I going to know what to do next here? And the truth is, it is practice. You have to do a lot of them to be sure. And you kind of get, sometimes you'll remember, oh, I did this before. Or sometimes it's an instinct that develops over time. So what I'm going to say is, I'm going to say 8 can be written as 7 plus 1. And of course, you can see where I go, why I choose that, because obviously I want to prove it's divisible by 7. So I multiply my 2 to the power of 3k minus 1 by my 7 to get 2. It's 7 times 2 to the power of 3k minus 1. I also multiply by the 1 to get 2 times 3k minus 1. But of course, now I'm happier because now I have what my 2 to the power of 3k minus 1 plus 3, which is exactly what I had up here in step 2. I know that's equal to 7 times a. Okay, so I can, instead of having my 2 to the power of 3k minus 1 plus 3, I can call that 7a. I still have my 7 times 2 to the power of 3k minus 1. The bit in orange is divisible by 7. The bit in yellow is divisible by 7. So therefore, the whole thing is divisible by 7. I have proven it's true for n equals 1, the base case. Assuming it's true for n equals k, I've proven it's true for n equals k plus 1. Therefore, by induction, I have proven that 2 to the power of 3n minus 1 plus 3 is divisible by 7 for all n an element of the natural numbers. So that's 15 marks. Some people still won't like it at the end of that explanation, but others will be starting to think, hold on, maybe that's not so bad. Okay, let's go to question 3.